On Earth, plants convert CO2 into some of the essentials we need to survive. On Mars, there are no plants, but there is a lot of CO2. So what if there was a way to use Martian CO2 to create the essentials we need to survive away from Earth? This is exactly what the CO2 Conversion Challenge aimed to do. NASA challenged teams to find a way to convert carbon dioxide into sugar molecules that could feed microorganisms in bioreactors. These multifunctional bioreactors could act just like little farms on Mars, creating resources we need to survive off Earth, on demand. Food, medicine, vitamins, and even construction materials. Now, 3 teams have successfully completed the CO2 Conversion Challenge, and today we announce the winners. These winning technologies could allow future astronauts to manufacture products using local resources on Mars, and one day even benefit us on Earth, allowing us to make use of the carbon dioxide that's all around us. Now, one day, farms of bioreactors on Mars could behave a little more like farms of plants on Earth.
Good afternoon. Hello, my name is Amber Jacobson, and thank you for joining us today to announce the winners of our CO2 Conversion Challenge, a challenge where we've asked teams across the country to advance the capabilities of our current systems to convert carbon dioxide into compounds or sugars that can be used to biomanufacture products that are critical for space missions. Products like food, nutrients, even medicine. In this phase of the competition, teams have moved beyond ideating and design and have gone on to build and demonstrate these systems. We've got an exciting lineup leading up to awarding our prizes today for this challenge, including hearing from NASA's Senior Climate Science Advisor, Dr. Gavin Schmidt. But first, let's hear from John Hogan, one of the judges for this challenge, on why this challenge is so important and how we'll be able to push companies to make unique products to serve this need.
The CO2 Conversion Challenge is pushing science and industry to be able to make more and more complex and more useful compounds from carbon dioxide. When we're exploring space, it's very expensive to bring things with us. Being able to use CO2 that we can get from, let's say, the Martian atmosphere, or from the CO2 that we breathe out every day, we can use these local resources to produce things like nutrients and medicines and many other products. The hope is eventually we'll be able to make nearly all the products that we need that are organic in nature from carbon dioxide and water. The CO2 Centennial Challenge is really important because this has been pushing companies to make new products that they otherwise wouldn't have thought about making. We can extend this process to make even more and more materials that we need here on Earth. Many of the ways that we manufacture things today actually produce large amounts of carbon dioxide, which we understand to be contributing to climate change. Ultimately, we hope to use this process to do very large-scale manufacturing. For instance, the making of cement produces a lot of carbon dioxide. Imagine that we can reverse that process, where we're using carbon dioxide to make cement or to make the binders that we need to make our buildings, to make our roads. Being able to pull carbon dioxide out of the atmosphere and put it into products would allow us to actually reduce the amount of carbon dioxide that would be in the atmosphere. Now that we're announcing the winners of this CO2 Conversion Challenge, I'm extremely excited to see where it's going to go from here.
Thank you, John, for those words. So now that we've heard why challenges like these are so important, let's turn to Dr. Gavin Schmidt, NASA's Senior Climate Science Advisor, to learn more. Gavin, how are you doing today?
I'm pretty good. How are you?
I'm doing well, thank you.
Great. So I'm a climate scientist, and the kind of carbon dioxide challenge that we face here on Earth is somewhat different to the one that we're addressing here. But I think it's very interesting to point out how the thread of carbon dioxide particularly runs through almost everything that NASA is doing. Here on Earth, we are tracking the sources and amounts of carbon dioxide in the atmosphere because of its role as a greenhouse gas, because of its role as a fertilizer for plants. and its impact on climate. And as you're aware, temperatures are warming and the seas are rising, and weather is becoming in some places more extreme because of the increases in carbon dioxide on Earth. But when you go further afield, when you go to Venus, you see, we've got way too much carbon dioxide, and that's creating a climate on Venus that's unlivable, perhaps not in the clouds. Or you go to Mars, we don't have enough carbon dioxide, and so that planet has a very thin atmosphere, is very cold. And when we're in space, carbon dioxide is one of the things that we produce too much of ourselves. We eat food and convert that food into sugars and then use it and then breathe it out as carbon dioxide. That produces a problem in confined spacecraft that leads to carbon dioxide increasing quite rapidly unless you find a way to pull it out of the air. On Earth, we're also researching ways to pull carbon dioxide out of the air. But the scale of what's required to compensate for our centuries of burning fossil fuels on Earth mean that you're looking for a slightly different kind of engineered solution than is appropriate for this. But this challenge here is looking at carbon dioxide in a totally different context. It's looking at it as a source of carbon, as a seed for producing more complex carbon molecules, sugars particularly, but eventually many different other kinds of molecules that could be useful to us in space. But the connections between what NASA is doing in space, what NASA is doing on Earth, are really quite profound, I find it immensely satisfying to work for an agency that covers the CO2 challenge across all of these different facets, whether it's at the South Pole, in the ocean, and in the atmosphere on Earth, or in Venus, or Mars, or in space, and working towards dealing with whatever carbon dioxide challenge there is. And this is a very neat challenge, and I think we're going to love to hear about what the solutions that have been engineered look like. So thank you very much for having me on, and I wish you all the best in taking forward and making our carbon dioxide challenges a little bit less challenging in the future.
Thank you so much, Gavin. Now it's the moment you've all been waiting for. It's time to announce our winners. To do that, we have NASA Ames Research Center Director, Dr. Eugene Tu, to do the honors. We're so excited that you could join us today, Eugene.
Thank you, Amber. And it's always tough to follow Gavin because he has already described the impact and meaning of this so well, but I'll try. So I'm really honored to be here to support the awards ceremony for the Carbon Dioxide Conversion Challenge. Being from one of the NASA research centers, we know all too well the importance and impact of these challenges and what all of you have accomplished. We know that the ability to take advantage of in-situ resources, living off the land or the air in this case, will be a game changer for the future of space and planetary exploration and potentially settlement. So, for example, here at Ames, in addition to being one of the key drivers for this challenge, as you heard from the video from Dr. Hogan, we are working on the Viper mission, which is a resource prospecting mission at its heart, scheduled to go back to the moon in 2023 to explore how we can potentially use the water ice that we know is there. So on behalf of NASA, I'd like to congratulate all the participants of the Carbon Dioxide Conversion Challenge. The second phase of this challenge opened nearly 2 years ago to build and demonstrate the physical conversion of carbon dioxide into sugars. We are incredibly excited to see the demonstrations conducted by these teams to help us biomanufacture critical resources for future planetary missions. The technology you, our participants, are developing will for Mars for benefit for future robotic and human exploration. Additionally, we look forward to seeing how what you've developed can one day unlock innovation and economic opportunity or inspire other makers and solvers to make a difference in their own way. We have 3 winners to announce today, each winning a slice of the $650,000 prize purse. Additionally, each team is eligible for a bonus prize on top of their winnings. So a little bit of drum roll, please. The winners of the Carbon Dioxide Conversion Challenge are the Air Company from New York, New York, Hego Energetics from Thousand Oaks, California, and Team Sweet from the University of California, Berkeley. Each of you will take home $216,667, even shares of the $650,000 prize. And since this is NASA, for all of you who do math precisely, there is a dollar difference there, but we'll figure that part out. Additionally, Air Company will receive a bonus prize of $50,000. Hego Energetics and Team Sweet will each receive bonus prizes of $25,000. Congratulations to all our winning teams on your achievement. We are beyond excited to see how this will evolve and the implementation of this new technology. Thank you to everyone involved in the competition and for your contributions to advancing space exploration.
Eugene, this is so exciting. Thank you so much, and congratulations to our winning teams. Yay. Thank you. Soon, we're going to let you hear from these teams along with one of our challenge judges, Morgan Abney. First, though, let's dive a little further into these teams' winning solutions.
Air Company is a technology and lifestyle company in New York City, and we've developed technologies that try to help the world by turning carbon dioxide into value-added products.
The goal of me and staff working on this is to give him and to give other people a platform to actually take their ideas, try to make them a reality, and try and get them out into the world as well. It's just about innovating and solving a problem, and we're trying to solve problems here every day, and we're trying to solve the problems from out there every day as well.
If you work out all the uses of ethanol and all the carbon emissions of ethanol, if you were to replace that with our ethanol, we could have a major impact toward fighting climate change.
Hi, this is Wilson Hego. I'm team leader for Hego Energetics. Our team, which includes key team members Randy Hatfield and Alan DeRosset, has expertise in the areas of energy conversion and industrial catalysis. We work on the development of carbon negative technologies, such as the production of green hydrogen from biogas and the capture of carbon dioxide from point sources, as well as the atmosphere, and also the production of liquid fuels from the captured carbon dioxide. Our mission is to reverse global warming and to leave a habitable planet for future generations around the world. Thank you.
We're here at the College of Chemistry at the University of California, Berkeley, where our team is located. We are Team Sweet, which stands for Space Sugar with Electrochemical Energy Technology. Our team consists of Professor Peidong Yang, Doctors Mike Ross and Ethan Lee, and myself, Stefanos Estellos Blanco. And together, we have devised a method to electrochemically convert CO2 to sugars to provide chemicals and materials to manned space exploration missions for NASA. We are thankful to the judges and all the NASA folks for organizing this exciting challenge.
Thank you, teams, for those videos. Now, we're going to spend a little bit of time talking with these brilliant teams and one of our stellar judges, Morgan Abney. Starting out, though, I think the thing that we'd love to hear a little bit more about is your winning solutions. Can each of you take a moment to explain how your solution works? Wilson, you want to go first?
Sure, I'll start. Yeah, thank you. Yeah, so the basic solution is we start with the electrolysis of water to produce hydrogen, and then we combine the hydrogen with the CO2, which will be captured to make methanol, and then the methanol is the methanol is basically something that's very widely available. I'm trying to make this explainable so even high school kids and middle school kids can understand. And then the methanol is converted to another chemical called formaldehyde. Formaldehyde is a chemical that's, for example, if you ever dissected a frog, you know about it. And then the formaldehyde is that's converted to sugars in the reactor. So that's the basics of our solution.
Thanks, Wilson.
Yep. I can jump in next.
Go for it.
From Air Company, we also do water electrolysis, create alcohols from carbon dioxide. We do that over proprietary catalysts that we produce in-house. We dehydrate those alcohols and then perform an aldol reaction. And that just assembles the individual carbons together, the 6 carbon sugars, to make glucose and other sugars.
Sweet. Stefano, what about Team Sweet?
Yeah, great. Well, first of all, thanks so much for putting the ceremony together. We're very excited. Our technology consists on CO2 electrolysis, which basically means we take electricity and transfer electrons to CO2. That CO2, we make reactive intermediates that then are reacted together to form the carbohydrate sugars.
Awesome. So, Morgan, seeing this new technology built and now demonstrated, what do you think is next for it? Where do you see this technology going in the next 5 to 10 years?
Yeah, so all of these are really, really exciting technologies, right? And they all taking that first step, a big step, but the first step in this process. So I would say 5 years, I would love to see these technologies demonstrate automated from start to finish, going from CO2 to the glucose or the other sugars that they're producing. I would further like in that 5 years for them to demonstrate these in a relevant environment for space systems. We have an incredible space station right above us, the laboratory. These teams, I think, are the right folks to be able to take us up there and demonstrate these on ISS, and potentially one step further to the rover mission. In 10 years, I would love to see these technologies integrated with the next step in the process. Not only going from CO2 to glucose, but now useful products, plastic, or food, medicines. And I think that these are the kind of innovative teams that we need to be able to get us there.
Thanks, Morgan. So, to our teams, what do you guys feel the next steps are for this technology and your team as well?
Scale up, I would say, and that not only goes for us, but I imagine I'm talking for Wilson and Stefano as well. Carbon dioxide conversion problem in space is a big problem, but there's also a massive carbon dioxide problem here on Earth with climate change.
Yeah, exactly. That's kind of the name of the game, is to be able to implement the solutions on Earth and as fast as possible, because climate change is a pressing problem for all humanity.
Yeah, I definitely agree with Wilson and Stafford. I think scaling up and engineering the device to a point where it makes a difference would be incredibly transformative. I also think that specifically for this technology, making sure that the sugars we create will actually feed into the processes that require these sugars.
Let's say, Greg, you're here too. Do you have any thoughts on that?
No, I think all of those teams hit the nail on the head, right? Like we're trying to push the needle here on Earth, and we're really trying to what we're doing here to be able to be scalable for future exploration as well. So we're really stoked to be a part of such a great cohort, and the support of NASA has been incredible. So thank you.
Thank you. So Morgan, I understand that you're doing research into this very field. How is this challenge helping your research?
Well, my area of expertise, life support, crew systems, right? We're trying to get people sustainably on the surface, long duration, the moon and Mars. And as I mentioned before, this is the first step. Biomanufacturing could be an enabling capability that we would take to those places to allow us to stay long term. And so I'm super excited to have these types of technologies feeding into those next steps that we're going to need to be able to do that.
Thanks, Morgan. And so here's a question about challenges. So for our teams, what kind of challenges did you run into when building and demonstrating your systems? And what motivated you to keep going?
Well, for us, I mean, there were many challenges. One of the challenges was that COVID happened, and then we needed to find some way of detecting glucose, and then there was nothing around. Actually, a local university offered to their equipment, but they unfortunately couldn't access it because they were closed. So we had to devise. We actually found that basically the technology that is used for glucose, when you go ahead, diabetics, when they go ahead and measure the blood sugar, we found out that we could use that technology if we did some slightly tweaking, and so that's how we kind of got around some of these challenges.
I would say COVID posed a pretty big challenge, I imagine, for all of us. Not only on the detection side, but just in terms of being able to get to the lab and be able to progress quickly. We actually had kind of switched our technology to create sanitizer for a lot of COVID. So that was our focus, and we just had to kind of go on the back burner for a little while. But then we quickly picked it right back up when we were able to have analytical facilities and things. Stefano, I don't want to steal your thunder though.
Yeah, no, COVID was definitely had a big impact on our ability to perform our research. One thing that, in addition to actually detecting what we have produced, was difficult. Just putting all the different pieces of the technology together, have different pieces feeding into a downstream process to make sugars, and just making sure that it's all compatible with each other.
Yeah, and one note that I don't think anyone touched on here is what keeps us going, and I'm sure I can speak for everyone here, but it's innovation, right? And that's what keeps us all working on everything that we work on, and I think that's what keeps all the NASA folks working on what you guys and girls do on a daily basis as well, and that's what keeps our motivation and our teams moving forward.
Well put, definitely so. So last question. As you're all aware, the CO2 conversion challenge isn't the only challenge that NASA has going on right now. We have some more of them. And there's challenges available for others to participate on nasa.gov/solve. What advice would you give to another team or person looking to compete in a NASA challenge? And Morgan, as a judge, I'd love to hear your thoughts on this too.
I would say just go for it. The first step is on paper and design, or at least it was for this challenge, and I believe it is for many other challenges. But please, Amber, correct me if I'm wrong. And so you don't need to put in a lot of your. You don't need to have a ton of like resources to be able. You don't need to have a laboratory to be able to just put your foot in. And once you win that first that first phase, that really can catapult you toward winning the next phase.
Yeah, I would say, yeah. For us, I'd say just find smart people to work with, you enjoy working with, and then just keep at it until you succeed.
Yeah, for me, I would voice a similar thing in having the right team is very important. We're all representing our respective teams. At least for Team Suite, it was comprised of me and other graduate students and postdocs in our academic lab. And it's just incredibly important to have people with diverse skill sets and expertise.
Yeah, and I would just say, what's great about these challenges is that anybody can respond, right? We get responses from all over the world, and you never know where the next incredible innovation or idea is going to come from. And so my advice to anybody who even has an inkling of an idea is to and try, because you never know if yours is the idea that nobody's ever thought of before. That's my advice.
Sound advice, folks. So that's all the time we have for questions today, but I do want to invite each of our teams, as well as Morgan, to give us some final thoughts. Air Company, do you want to start us off?
Yeah, absolutely. We really appreciated and we really do appreciate the focus on CO2 conversion in space, because like solar panels first came about from being used on satellites in outer space. It's a really good way to commercialize technologies that are really high tech and need a lot of development to be widespread.
Yeah, I can go next. I want to thank NASA for allowing us to participate in this contest. This is an important contest, not just for developing technology on Mars, but for Earth. And I think we need to, all of the teams going forward, that we will be working on developing these carbon dioxide capturing technologies going forward. Thank you.
I also would like to thank NASA for everything that they've done to help us in this competition. I also think the importance of these competitions is to highlight the technologies that are popping up to fix carbon dioxide, both in space and here on Earth. Climate change is a generational challenge, and we need all the people that we can get to work on it. And lastly, also like to take a moment to thank the rest of my team suite, Sheena, Mike, Ethan, and our research advisor, Pyong Yang.
All right. Well, guys, I just want to say thank you to all the teams that did such an incredible job on this. It has been such a pleasure to watch you guys go through this process. And I cannot wait to see what the next step is for all of y'all. So thank you guys so much.
And thank you for all of your answers. We are so excited for this new technology that you developed. Before we sign off, I'd like to introduce Anzi Rahman, Centennial Challenges Program Manager, for some closing remarks.
So, good afternoon, everybody. It is a pleasure to close this ceremony with a celebration of the teams that participated. One way or another, you have heard from me throughout this process. So, and you have heard from Dawn Turner, who has been keeping this competition going. So, thanks to her, to our judges, Morgan for participating today, to NASA headquarters also for all their support of this competition. But today I want this to be about the teams, and I want to shine the light on you guys. The information that you have shared with the public today has been amazing, and we really, truthfully, are looking forward to seeing where you go with the things that you have developed. I was impressed with the kind of solutions each of your teams came up with. They were all different, but they all had incredible strengths and applications that will get you, I suspect, in different ways. So that's also exciting to see, how we move forward with those. And anyways, thank you so very much. Thank you to Eugene and to Gavin for the words before we started. And again, this is a celebration of you guys. We're here to help you. Centennial Challenges team is very eager to continue to work with you unofficially as we close the competition. Our part of the competition, our working with you day to day is going to end, but we are very good about keeping up with our teams. So just don't be surprised if we continue to call you and check how you guys are doing. So again, congratulations, and anything we can do to help you from now on, here to help. Thank you very much.
Thank you.
Thank you. Thank you, Mansi. Thank you, everyone. And thank you to our viewers for tuning in today for this exciting announcement. If you have questions for our winners and our challenge experts, be sure to tune in at the top of the hour in just 30 minutes time for a Reddit AMA and the R-Space thread. Otherwise, we're so happy that you could join us today for this announcement, where we learned how teams were able to build systems that could convert carbon dioxide into sugars that could help manufacture products for future planetary missions. As always, if you're interested in participating in future NASA challenges, please visit nasa.gov